So hey guys, hello and welcome back to my channel. This is me Prithvikam Paikrai and you are watching Step 2 Math. So today in this class we will be discussing about the rational numbers and their decimal representations. So basically in the last classes I have told you what are rational numbers. So let me write this definition once again. So it is denoted by Q and these are all the numbers in the form P by Q where P and Q are integers and Q is not equals to 0. Okay, so these are called my rational numbers. So as we know, real numbers, so they are divided into two parts. So one is the collection of all rational numbers and the other one is irrational numbers. Okay, so I will be saying the collection of all rational numbers and irrational numbers forms the real numbers. So let me give some examples. So you can say 1 by 2, 2 by 4, 1 by 3, 3 by 8 and so on. So these are some examples of rational numbers. Similarly, root 2, root 3, root 5 and all these numbers are called my irrational numbers. So rational number means it is given in the form of P by Q. So also I can say the decimal representation of any number is a rational number if it is satisfying some properties. So one of the property, that means if the decimal expansion is terminating, or non-terminating repeating. Okay, so non-terminating repeating, then I will be saying that type of decimal I can represent that in form of fractions and or that in terms of P by Q. So we can say, okay, these two type of decimal representation, they are actually the example of rational numbers. So if it is non-terminating and non-repeating, then I will say, okay, so these type of numbers, they are called my irrational numbers. So I can say, give some examples for terminating. So it is 1.2, 1.35 and so on. Okay, so similarly non-terminating repeating, I can say 1.333, 1.4545 and so on. So all these numbers are my or I can write this is equals to 1.3 bar, this is equals to 1.45 bar and so on. Okay, so these are called my non-terminating but repeating. So you can see 3 is repeating here, so 4545 is repeating here. So similarly, if I will I want to give some example. So 1.01, 001, 001, 01 and so on. Okay, so this is a you can see it is non-terminating and non-repeating. So this is the example of a irrational number. Okay, so these are the fundamental things about the rational numbers and irrational numbers, and this collection of the rational numbers and as well as irrational numbers. So that will be giving me the real numbers. So in last classes we have discussed about how to prove a number like root 2, root 3, root 5 to be a irrational number. Okay, so today we will be discussing about how I can say whether a rational number is terminating or non-terminating. That means how I can find the decimal expansion of a rational number and say, okay, that number is terminating or non-terminating. It is terminating or non-terminating repeating. Okay, so let us take one by one. So, but let me give you one example. So let us convert that question into fractions. Okay, so let me write this. Suppose I am having x is equals to 1.5. So the question is, convert this x is equals to 1.5 into fractions. That means in the form of P by Q. So what will we do is that, so x is equals to 1.5. So we will be multiplying 10 to both the sides. So I will be getting 15. So now you can see the right side will converted into a whole number. So that implies when it will be a whole number, then I can say x is equals to 15 by 10, or I can reduce that, it will be 3 by 2. Okay, so it is 3 by 2. So you can see this x is equals to 1.5. I can write this as 3 by 2. Okay, so that is the fractional representation of this decimal of this 1.5. So similarly, if I be considering x is equals to 1.5 bar, that is nothing but that is 1.555. That means 5 is repeating here. So what will we do is that again I will be considering, okay, so that implies 10x is equals to 15.555 and so on. So here you can see this is not a whole number. Okay, this is not a whole number. But if I will be subtracting x from this 10x, then that will give me a whole number. So that implies I can say 10x minus x is equals to 15.555 and so on minus 1.555 and so on. So I can say this implies 9x is equals to 14. So that implies x is equals to 14 by 9. Okay, this is equals to x is equals to 14 by 9. So you can see these are co-primes, and I can say okay, the fractional value of this number x is equals to 1.555 and so on is 14 by 9. Okay, so let us take another example that x is equals to 1.534. Okay, so that means the bar 34 is repeating. That means I can say this is equals to 1.53434 and so on. So how will we writing the corresponding fractional value for this x? So in the same technique, I will be using the same technique. So 10x is equals to 15.3434 and so on. Okay, so obviously this is not a this right side is not a whole number. So I will be consider okay. But if I will be subtracting x from 10x, so again I cannot get a whole number. So what will I do? Again I will multiply 10x 10 to both the sides. So it will be 100x is equals to 153.434 and so on. So you can say okay, if I will be subtracting x or 10x in 100x, so I cannot get a whole number. So again I will be considering the step, that is I will multiply again at 10 to both the sides, so I will be getting 1534.3434 and so on. Okay, so now you can see 10x x it is not a whole number, 10x is not a whole number, 100x is not a whole number, 1000x is not a whole number. But if I will be subtracting 10x from 1000x, so let me see, yes, so I will be getting 1534.3434 and so on minus 15.3434 and so on. So you can see it will be so 1519. Okay, so it is 1519. This implies it is you can see it is 990 x is equal to this. This implies x is equals to 1519 by 990. Okay, so by this you can find the fractional value of this x is equals to 15.3 is equals to 1.53434 and so on. Okay, so in earlier classes, that means in class 9, actually you have read about how to find the fractional value of any decimal representation. Okay, so today we will be just discussing 3 theorems, and using that 3 theorems we will be saying okay, which type of fraction will be terminating, which will be non-terminating repeating type fraction. Okay, so fine, or that will be having the non-terminating repeating type of decimal representation. So fine, so let us write this theorem. So basically in this part we are having only 3 theorems, so whose statement we have to remember. Okay, so let me give the statement for this theorems. So first theorem, it says if x is a rational number, if x is a rational number, okay, the theorem says if x is a rational number with the decimal representation that terminates, then x can be written in the form, then x can be written in the form P by Q, where P and Q are co-primes, and Q has a prime factorization of the form 2 to the power n into 5 to the power m, 2 to the power n into 5 to the power m, where n and m are positive integers. Okay, where n and m are positive integers. So that means it is saying if I am having a rational number with a decimal representation and the decimal representation terminates, that means if I am considering a number, suppose x is equals to 1.5 534. Suppose this is 1.5534. So I will be saying yes. So the number, because the decimal representation terminates after the fourth place of the after the decimal. So I will be saying okay. So if this is my x, so this will be terminating. This implies this I can write in the form something by 2 to the power n into 5 to the power n for some positive integers n and m. So let us write this. So it is equals to 15534 divided by 2 to the power 4 into 5 to the power 4. So you can check this. So and then after will be just see what will be the what are the possible factors or possible common factors in the numerator and denominator. So you can see we can divide numerator and denominator by 2. So you will be seeing it is 7. So 7, 6, 7. Okay. So you can say it is 7764 by 2 to the power 3, 5 to the power 4. Okay. So I can write, if the number terminates, then I can write this in terms of this. Okay. So what I basically do is here that, so I will be considering how many numbers are there after the decimal place, and I will be multiplying 10 to the power that number. So if it is here, it is 4, if it will be k, so I will be divided multiplying 10 to the power k, and will be dividing 10 to the power k simultaneously, so that I can get a number in the terms of fraction. Okay, in the terms of fraction or in terms of p by q. Okay, so and you can also see. Okay, so that is 7767. Sorry. 7767. Okay, and you can see these are co-primes. Okay, so this I can verify this statement by taking this example. So next I will be considering the second theorem. So this theorem says the converse part of this. That means if x is equals to p by q is a rational number, so is a rational number such that the prime factorization of q is of the form 2 to the power n into 5 to the power n, 2 to the power n, 5 to the power n for some positive integers n and m, then the decimal representation of x terminates. Okay, so this is basically the converse of this part. So that means if I be considering it is suppose 3 by 100, so that is 3 by 2 to the power 2 into 5 to the power 2. So you can see this will be 0.003. Okay, so it is 0.03. That is fine. So you can see if it is in the form of 2 to the power n into 5 to the power m, so it will be the decimal representation will be terminating. Okay, so these are two examples. These are two theorems, and you can justify this theorem by using this example. Okay, so next we will be considering the another theorem. So that theorem says if that theorem says if x is equals to p by q is a rational number, this is a rational number where p and q are co-primes, then I can say, okay, if x is a rational number where p and q are co-primes, then x is non-terminating and repeating if q is not in the form 2 to the power n into 5 to the power n. Okay, so let x is equals to some 3 by 9. Okay, so that means it will be equals to 1 by 3. So you can see this will be giving me 0.33. So it is non-terminating repeating, because here I can check here that, so the denominator term, it is not in the form 2 to the power n into 5 to the power n. So not in the form means q is not in the form means I will do the prime factorization of q. Okay, so the prime factorization of q is not of the form 2 to the power n into 5 to the power m. So these are the three theorems which are most important for this part, how to say a number is terminating or non-terminating by using the question only and without solving that problem. So let me give some problems. So by question is, by not solving the question, by not solving the problem, find which of the following are terminating or following has terminating decimal representation and find its decimal representation. Okay, find its decimal representation. Fine. So let me give one a question. So suppose it is 3 by 15. Another one is suppose it is, let it be 2 by 25, then 18 by 100. Okay, let us consider these three questions: 3 by 15, okay, 2 by 25, and 18 by 100. So for the first one, x is equals to 3 by 15, that is equals to 3 by 3 into 5. Okay, so that is equals to 1 by 5. Fine. So it is 1 by 5. So I can write this is equals to 1 by 2 to the power 0 into 5 to the power 1. So this implies as the prime factorization of 5 is equals to 2 to the power 0 into 5 to the power 1. This implies 1 by, this implies 3 by 5, or 3 by 15. This implies the decimal representation of 3 by 15 terminates. Okay, so it terminates. Then what will be the value of this decimal representation? So what will we do is that, so 3 by 5 is equals to 1 by 5. So we will be multiplying 2 in the numerator as well as denominator. So I can get 2 by 2 into 5, that is 2 by 10. So now it is easy to write. So it is in the decimal form. So it is 0.2. Okay, so it is 0.2. So similarly, next consider the question second. So that is 2 by 25. So that is 2 by, you can see it is 5 square. Okay, so it is 2 by 5 square. So you can say, okay, this implies 5 means 25 has the prime factorization, as 2 to the power 0 into 5 to the power 2. This implies 2 by 25 has a decimal representation that terminates. Okay, that terminates. So fine. So then what will be the value? So again you can say, okay, 2 by 25. So it will be equals to 2 by 5 square. So what will you do is that you will multiply 2 to the power 2 in the numerator as well as in the denominator. So 2 into 2 square by 2 square into 5 square. So it will be 8 by 100. So this will be equals to 0.08. Okay. So this will be 0.08. So basically what I have done here is that, so I am making the denominator in terms of 10, 100, 1000, something like this. So here you can say, okay, here is 5 square. Okay, if I will multiply 2 square, then it will be 2 square into 5 square. That means it will be 100 here. So so that I can just multiply the numerator value, and then I will be using the decimal representation of that for the numerator by dividing the denominator value, so that we can get the required answer. So similarly you can check for 18 by 100. So this will be also terminating, and it will be giving me the value. It is 0.18. Okay, so you'll be getting the value 0.18. point. So this is a task for you. So actually this is all about our rational numbers and their decimal representation. Okay, so you can go through some other problems from the NCERT book. If you are having any doubt, so you can comment me in the comment section. So for today, it is all about our real numbers. So in the next class, we will be discussing about the polynomials. So for today, thank you all and stay safe and stay happy.